in this video, we will be talking about momentum and impulse. We'll be solving questions related to them. So for momentum, the basic definition is it is the mass in motion. When we say motion, it's associated with the idea of movement. Uh, Something's moving. So yes, that's for momentum. For impulse, this is the amount of force that's applied to an incoming object at the moment of impact. This can also be, impulse can also be defined as the amount of force that is opposite of an incoming object. So basically what it takes to make it stop, this incoming object stop. So regarding the formula for momentum, it is in some textbooks, it is abbreviated as with the small letter p, but it can also be written as a p with a small letter p with a horizontal line in the middle for a reason. There has to be a reason why. But yes, in class we were taught that momentum is written that way. So it is equal to mass times velocity, basically. And the unit for momentum is kilograms times meters per second. So kilograms corresponds to mass and the velocity, the meters per second. So for impulse, on the other hand, um, it is abbreviated with the letter capital J. Um, the unit is Newton seconds. So Newton for force and times the time, which is seconds, in seconds. So another thing that you have to know is the impulse momentum theorem. It basically states that impulse and momentum are conserved. Um, the word conserved is the same with the idea on the law of conservation of energy, stating that nothing is lost, no energy is lost. Here, it's the same thing. Um, Other than energy, impulse and momentum are also conserved, so they're not lost. They can be transferred, rather. Speaking of transfer, there's another topic that we did not really touch that much in our class. Although it's part of the syllabus, we didn't really cover it according to the intended schedule. It's already the fourth quarter or the second part of the second semester, and yeah, I'm not sure if our teacher will continue on that path. The lesson is basically about collision. We did touch it somehow, but I'm still yet to look at my archives if we answered in class the questions. So, without further ado, uh, impulse momentum theorem. There is this equation, impulse is equal to momentum. And therefore, from there, J, we all know that it's equal to Ft, the force times time, according to this. And P can be extended as M times V. So we have something like this. So they're basically equal to each other. Let's answer some questions. So to stop a moving mass, it would take the same amount of impulse to counter the amount of momentum. To counteract the momentum, the impulse should be either to maintain the impulse, a large amount of force should be applied in a short period of time. Or another way is to provide a small constant amount of force. It has to be applied in a longer period of time. It makes sense. It's logical to understand. Either you apply the force greatly, but in a short period of time, or you apply little force, but it's progressive. Wait, not really progressive. It says here constant. But yeah, the small force should be maintained in application for a longer period of time. That time depends on the mass and the other relevant factors. Okay, let's solve number 1. It kind of makes sense. Momentum is known to be the mass in motion, right? So in order to counter the momentum value itself, the impulse has to be equal. If the momentum is greater, then the object wouldn't stop moving. Since the force that ought to counter the force with respect to the object itself, the incoming object, um, basically, yes, it has to be greater. I mean, yeah, just equal. If it's greater, then I'm not sure how that's going to be properly explained. The stopping force is greater than the force of basically the mass in motion. Anyways, number one, the momentum of a 3,000 kilogram truck. So the mass is 3,000 kilograms. Momentum is said to be 6.36 times 10 raised to 4 kilograms times meters per second. So at what speed is the truck traveling? So what we mean by speed is basically velocity. That's the missing value. So P is equal to mv, such that we know what P is as well as the mass. We're looking for velocity. Therefore, our formula ought to be calibrated this way. So V is equal to P. P is 6.36 times 10 raised to 4 kilograms times meters per second. Mass is 3,000 kilograms. Okay, what is the answer? $21.2. I believe this is the answer. And the kilogram unit will be cancelled. This is what we have left. It makes total sense that our unit corresponds to velocity. Okay, number 2. A 0.40 kilogram object is moving on a frictionless surface with a speed of 30 meters per second. A force of 2 newtons is applied continuously until the velocity of the object has been reversed. Okay. So how long was the force applied? I believe this is going to be an impulse kind of problem. So let's bring out the impulse formula. So J is equal to F times T. So I believe time is missing, since what's being asked is how long. That's the key word, the key phrase rather. So F is what? I believe that's the 2 newtons. Okay. Okay. We know that in the impulse momentum theorem, J is equal to impulse is equal to momentum. So we do have the values needed to look for momentum. So let's do that. So 0.40 times 30 is 12. And that could also be equal to impulse. We have the value of impulse. We have the value of force. Now it's time to substitute. Anyways, we have to calibrate first the formula to our own liking. Here it is. 12 kilograms meters per second over force. Force is 2 newtons. So how do you write force in another way? It could be written as kilograms times meters per second squared. And it makes sense. Since time, the unit, you know it as seconds, right? This will be 6 eventually, the number. I believe these will cancel out. No, except that. So what we have left is seconds. So yes, that's it for number 2. Number 3, yeah. Small rockets are used to make tiny corrections to the speed of a satellite. If a rocket has a thrust of 35 newtons, and is used to change the velocity of, okay, we have a mass. Damn, that's big. 63 centimeters per second. Okay, we have a velocity value. For how long should it be fired? Okay. I think this is also an impulse problem since time is only involved in the impulse formula. J is equal to Ft. Do we have the instruments to look for J such that P is equal to J? Let's bring out the formula for momentum. Mass and velocity, we do have both of them. So let's solve. 72,000 kilograms times 63 meters per second. $4,536,000. Okay, so that's what we're after is the fact that it's also equal, the momentum is equal to impulse. So again, we have the force and we have the impulse value. T is equal to J over F. T is equal to 4,536,000 over 35 kilograms times meters per second squared. Time is equal to what? 129,600 seconds. Is it? Wait a minute. This is cm. Sheesh, I think we have a mistake. This is why the time value is kind of crazy. This is why you have to convert to SI unit in the first place. Otherwise, all hell could be let loose. So 63 centimeters. This is meter dm cm. 2. Okay. 63 over 100 is 0.63. So yes, this is supposed to be our used velocity value, not the centimeters per second. Yeah, it has to be like that. Again, going back to the previous solution. Okay, so momentum is equal to impulse is equal to 45,360. I hope we're in the right track right now. Okay. And yeah, 1,296 seconds. So that's the answer. Number 4. So a 0.24 kilogram volleyball. So let's write that 0.24 kilogram volleyball. Approaches a player with a velocity equal to 3.3 meters per second. The player bumps the ball, giving it a speed of. Okay, so we have another velocity value. Okay. So let's say this is the initial direction and the speed of 2.4, but in the opposite direction. So that's that way. What average force did the player apply? Okay, so we're looking for average force. This is weird. I never answered this before. Yeah, my teacher didn't give an answer key for this. Sheesh. Yeah, I won't answer this part as well as this. Yes, I remember. I took the exam a few weeks ago. No, just last week, I think. Or yeah, maybe 2 weeks ago. Uh, I remember telling this to a classmate of mine. She also didn't answer these questions. And rightly so, because yeah, we remember teacher didn't discuss this one. Next is collision, right? What do I know about collision? Yes, the types of collision. Maybe let's touch a few concepts on this one. Uh, I'll just discuss about the types of collision. We won't be answering in this video questions related to collision itself. So, regarding the types of collision, we have three. First is elastic collision. This is the collision where the objects involved they remain as separated bodies after the contact or collision. The momentum is transferred from one object to another without losing any energy. You know what? I don't like reading. Find uh let's find something serious. I mean, a visual illustration. I know BYGU has um a proper illustration about it. I don't think it's here. Uh, let's just use this one. So, for elastic collision, I suppose there's elasticity involved. Um, According to this one, uh, objects remain as separate bodies after the contact or the collision. Momentum is transferred from one object to another without losing any energy. So this is a given. So energy is not lost. That is mentioned by the impulse momentum theorem. Uh, so yes, momentum is transferred. It makes sense in this. I'm not sure what this is officially called. The ball thingy. I know it's a science thing. I'm just not sure what that is called, but as you can see, the two balls from the left and right side, um, each from the left and right side, they are the ones that eventually move, like they swing, and after swinging, they come back and uh, the the balls in the middle, they eventually they basically transfer the energy um, to the other side. So let's move on to the next type. So in elastic collision, uh, as you can see, there are cars. So this is the kind of collision where, yeah, where is it here? So nearly elastic. Definitely not this. Perfect inelastic. objects involved are fused into one single object, move to the direction of the object with higher momentum. Okay, so yes, I believe mass is directly associated with momentum. The higher the mass, the higher the momentum. The bigger your vehicle is, the higher the mass, the more, uh, the higher chance your car is, um, your car has a higher momentum compared to another car whom you will be um, bumping into eventually, such as stated in this visual illustration. So for letter B, for the nearly elastic collision, this is the collision where objects involved are separated after the collision, but there is a loss of energy. Okay, I think that's important to note. We did not have this earlier. Uh, I'm not sure how this is supposed to bode well with the impulse momentum theorem, based on what it states, as well as the law of conservation of energy. They both state that nothing is lost, but here there is a loss of energy. I think that's worth noting. So yes, that's it for the types. Perhaps I could explain it better in future videos. But yeah, that's it. Primarily, our focus was to be on impulse and momentum, except for two questions right here. Yeah, such a shame. I couldn't answer them. But yes, that's it for this video. Thanks for watching.